physical design, I'm going to talk and I'm going to give a brief information about power planning. So before starting power planning, let me tell about how this physical design starts. So physical design, it requires certain input files for the process to be started. So in order to get those input files, among input files, netlist is also one of the input file. So in order to generate netlist, generate netlist, we start a process called synthesis. So what is synthesis? Synthesis is a process of converting RTL into an optimized netlist to get the targeted technology by meeting timing and power constraint. This is what synthesis is all about. And to start physical design, there are certain input files required. So in physical design, there are many types of input files used. They are RTL, SDC, library, left, netlist. So that what netlist we are getting from synthesis process, that is used as your input file in your physical design. Then after doing importing all those input files, we do a called a PNR flow. What does this PNR flow means? PNR is nothing but place and route flow. It's a part of ASIC. ASIC is nothing but application specific integrated circuit flow, which starts after synthesis. It is termed as backend processing ASIC flow. So after doing when we start in PNR flow, we are having different types of steps like floor planning, power planning, placement, CTS, routing, and we are having sign off also. Sign off, and then like we'll be converting all those. After doing all sign off and all, we are doing we are generating a GDS2 file. So that is all layout. Layout picture we are going to get into GDS2. So these are the process involved in your physical design. So like before we start physical design, like physical design is similar to a construction of a new house. Like how before building a new house, we need a house plan, so that we can understand how many rooms will be there, where they will be, and what is the leftover place. All these things we know. Similarly, in physical design, we also need a floor plan to decide where the macros to be placed and what is the leftover place, and where the standard cells to be placed. All these things we decide. So for a house planning, civil engineers are there, but for floor planning, physical design engineers have to take care. And then after floor planning, we are having power planning. So power planning, it's nothing but means to provide power to every macro and every standard cell and every cell that is present in your design. This is what a power planning is. Like a power planning is similar to your power supply connection in your house. While designing the power supply for houses, first the electrician will make sure that all rooms get connection, and or not. Likewise, power planning also, PD will make sure that entire chip will get a power supply or not. This is what a PD engineer does. Next, what is the next process comes as a placement. Placement, it's nothing but a process of placing all the standard cells that is present in the netlist by the tool into the core area. This is what placement is all about. Next, clock tree synthesis. Clock tree synthesis is nothing but it's a process of connecting the clock from clock port to the clock pins of the sequential cells in the design. Next comes routing. Routing, it's nothing but a process of creating physical connection between signal pins by following the DRC rules. This is all the steps required in our physical design. Now I am here to explain about power planning. So before starting power planning, let me tell what is power planning. Power planning is nothing but a process of adding metal wires to connect the power pins of all macros and standard cells to the external power source while meeting the IR drop and EM requirements. That is nothing but main motive of our power planning is to distribute the power to the entire chip so that the power is reached to all the macro pins as well as standard cell pins, and so that we should supply a power to those standard cells and the macros in such a way that we should meet our IR drop as well as EM requirement. That is, there should not be any IR drop also, and if we have to meet the EM requirements. So before going to IR drop and EM requirement, let me tell how does a power plan works and what are there in the power planning, how the power distribution is done. Let me explain those things, and then we'll go to what is meant by IR drop and what is meant by electromigration. So in power planning, it involves determining width, spacing, and the number of power nets, like example of VDD, VSS nets on the layout. Uses power network synthesis, and it must meet EM constraint for the wire and must have voltage drop, that is IR drop, less than allowed maximum at all location in the design, that is at least 5% of supply voltage. Next, goal of an power plan is to maintain equipotential VDD and VSS throughout the chip. Now, let me see the pictures of power planning. See, this is how your power planning is actually happening. So in IC, these are your VDD and VSS pins, and this is how power planning happening in chip level has been shown, and this is how your VDD and VSS connection to a standard cells will be there. This is how your VDD and VSS connections will be there. Next, this is power routes at chip level. Actually, there are two types of levels, that is chip level as well as block level. Right now, this is how in chip level power routes will be there. Block level and chip level, it's a different topic. I'll let you know about it later on. Next, this is how a power planning is all about, and it involves VDD, VSS straps, then core rings, IO cells, row straps, and core straps. So let me explain one by one how a power plan has been, power has been distributed in the design. This is just a picture. Let it be, and later on I'll explain each and everything in detail. See, this is how, as I said, there are two types of levels. This is now power routes in the block level, and this is how the power planning has been done in the block level. There is a different between chip level as well as block level. See, here we are having PG grids, and here this is how you place macros. So macros, that is what how this placing of macros and all is termed as your floor planning only. See, now this is how actually your power planning looks. This is how your PG grid looks. And here actually this power distribution is done in 3 stages. One is through rings, then through I was telling like how does this power planning involves and how the level of power distribution is happening. So power planning involves like calculating number of power pins required, number of rings and stripes, width of the rings and stripes IR drop. So how the calculation depends on the power consumed by a chip, total current drawn, current rating of a power pad, and current rating of metal layers, and the percentage of the current flowing through the metal layers. So level of power distribution happens in 3 types. One is rings, another one is stripes, and another one is rails. So as I am marked here, core rings. So core rings is nothing but it carries VDD, VSS around the chip. This is what carries VDD, VSS around the chip. As I have marked here, this dot lines, these are called as core rings. Next comes here straps. as I said here, PG straps, right? You can see one is in sky blue, other one is dark blue. Though these are nothing but PG straps which carries VDD VSS from rings. And there are some rails. Rails are nothing but connection of standard cell rails. That is nothing but connecting VDD VSS to the standard cells of VDD VSS. Those are called rails. So here you cannot see the rails. If you zoom in, you can see those rails. As of now, I have not shown any rails over here. This is how power distribution has been done in this thing. This is one kind of power planning. Next, we'll go further. How does power hookups for macros has been done? So power hookup for macro depends on the way power pins of macros are designed. They fall into one of the below three methods, that is ring pins, scattered pins, and long pins. Let's see how does this happens. Ring pins. So this is how the image shows with the power pins designed has a rings in M3 layers. As I shown you, right, how the rings are, they'll be around the chip. This is how rings will be there. Next, ring pins of macros are hooked up by running straps over the macro and dropping via between the pin and the strap. This is how it will do when we give when we give your straps. I mean when you construct your this thing. Next is scattered pins. What is scattered pins? The image shown of a macro with its power pins designed as a scattered pins. And so these pins, like as I shown in the previous picture, above there will be certain things like, you know, these are called as your scattered pins. These blue color are there now, small boxes, sorry. Those are called as your scattered pins. This is how your scattered pins is all about. And scattered pins like are hooked up by creating a macro ring around the macro and routing each power pin to it. Next comes your long pins. Long pins, like this is how your image shows of macros with its power pins designed like this. This is how your long pins is all about. Next, long pins of a macros are hooked up by running straps over the macros and dropping via between pin and the straps. Next, we'll move on to the topic called power hookup for standard cell. How does the power hookups for standard cells? So image shows that standard cells placed in two adjacent rows. Standard cells in adjacent rows are flipped to share the power pins. See, power plan example, we says that like this is a good power plan. Like actually we tell a power plan is good when it meets our requirement, like ear drop and EM requirement. Since I'm not touching those two problems, only we are telling how is that power has been distributed around this chip. Now according to my knowledge, now this one, what distribution of power, like whether it is a horizontal strips or vertical strips, the power distribution has been done correctly. Actually, power planning, like through metal wires, we are connecting macro pins and standard cells. That this is what actually what does a power plan means. So in likewise, these metal stripes are arranged in such a fashion that if metal 1 will be used as a horizontal and metal 2 will be used as a vertical, like horizontal HV methodology, the metal layers will be placed like alternatively. If odd metals have been used in horizontally, whereas even metals will be used in vertically. In this methodology only, the metals are distributed, metal wires are distributed in order to connect the macro pins and standard cells. And this one is according, by seeing the picture we can tell that the power planning is bad. Like how means some macro cells missing, crossing the power steps. So this is what a bad power planning picture is all about. Next, now comes to the picture about airdrop. So what do you mean by airdrop? Why does this happens in power planning? The voltage drop occurs because these wires, that is metal wires, what you are distributing, right? You are distributing your um, you're connecting macro pins and standard cells pins through metal wires, right? So these metal wires, these metal wires will have some resistance in them, which is a parasitic resistance. When a current goes through, there is a voltage drop in it. This voltage drop reduces the amount of voltage that a transistor will get later. This has to be continued, this has to be contained, because because bigger the voltage drop, transistors are going to get lower voltage and their performance will go down. In other words, gates will not gates will go, or performance will go slow down. This is what an airdrop creates an issue in your power planning and in your design. So how to how to um, how to reduce this airdrop, and we got just now got to know how does this airdrop occurs. Now by seeing some steps we'll get to know how can we reduce those um, how can you reduce those airdrop. So before going to this, let me say what is meant by airdrop. Like power nets that distribute power to the cells in a design have inherent resistance. Just now I said they'll be having some small resistance. This is what the statement is all about. Next, cell draws current from power supply through power nets. Due to the resistance of power net, current through it develops a voltage drop. So this is called a IR drop. So voltage at the pins of a cell is not the same at the voltage of the power supply. So for example, VDD is like we are having some VDD and VSS stripes, right? So one of the VDD, it is having 1.2 volt and resistance of power network is 12 ohm. Now current drawn by a cell in a design is how much? 100 milliampere. Next up, voltage drop in the power network will be how much? That is 12 into 100. That is nothing but resistance of a power network into current drawn by a cell. This is what is called voltage drop. If you do, you will get it as 120 millivolt. Now voltage drop, voltage at the power pin of a cell will be like 1.2 minus what is your voltage drop? So 1.08 volt will be your voltage at the power pins of the cell. This is how it has been calculated. Next, power network must meet IR drop goal, like typically 5% of the supply voltage. And actually this IR drop should meet within this range will be given by your foundry only. So according to that only we'll be maintaining the voltage drop in our design. So example, for supply voltage 1.2 volt, maximum IR drop in the power network should not be greater than 60 millivolt. This will be decided by the foundry. So accordingly, we'll be designing our chip. Next, in IR drop, there are two types of IR drops. So what are those types of IR drops? One is static, another one is dynamic. So what is static? Like, okay, before starting these things, as we know, power planning, it's all about nothing but distributing power to the macro pins and standard cells. This is what we got to know what is meant by power planning. But in power planning also, there happens a dissipation, not power dissipation. Why does this power dissipation happens? Because we use certain things, there is something side effects for that. Like for example, let me say, you'll be using your mobile, like without using your mobile also, there is some warmness in your mobile. When you touch, there is some heat coming out of your mobile, even without using your mobile. This is all because of your static power dissipation. Next, when you come for your dynamic power dissipation, another one is dynamic power dissipation. This, for this example I'll give you, like you will be playing games in your mobile and all. So after playing, there is some, you find your mobile to be heated up. There you find some warmness in your mobile. That heat dissipation is nothing but your dynamic power. And even that, that is the different thing, power dissipation. In airdrop also we are having certain types of airdrop, that is nothing but static and dynamic. So static, it's nothing but based on your average current demand, whereas dynamic, it's based on your dynamic or instantaneous current demand. Like its effect of switching of large number of circuitry switching, leading to peak current demand. Dynamic, even dynamic power dissipation is nothing but depends on your completely your switching activity of your this switching activity of a transistor leads to this dynamic this thing. So in older technology, static airdrop was good enough for sign off. Power network and non-switching logic provided sufficient decoupling capacitance to make average and peak current demands similar. In our design, this is how we do the analysis of your power plant, airdrop analysis. So airdrop analysis generates airdrop reports to enable the designer to check if airdrop goals are met. So typical APR tool supports airdrop analysis. So typical airdrop report for the design is this is how your drop will be. Where there is a red hot spot, that shows maximum airdrop in your design. In this design, there is not that much red hot spot in this thing. That means there is not that much droppage of airdrop. If there is a red color, red spot thing, that is means there is a huge airdrop in that place. This is how you do the analysis of your airdrop in your design. Next comes electromigration. So as I said, power planning is to maintain your, is to meet your EM as well as airdrop. Now let me tell what do you mean by electromigration. EM, it's a process of gradual displacement of metal atoms of a route in a design in an IC due to high density that causes metal ions to drift in the direction of current flow. So because of this EM, you got to know what is meant by EM. So if this EM happens, it results in open and shorts of metal routes. It happens over time. What is the solution for this one? So reduce the current density by increasing the metal width. EM rules specify maximum current density for a given width of the route. In other words, EM is nothing but your reliability of your mobile phone or this thing. Like for example, you can use a mobile phone for like 1 or 2 years. If our reliability is very good, if suppose if you are having very good EM, we cannot reduce completely EM, but we can have very good EM, like by using the remedies to resolve our electromigration, so that uh, um, so that our reliability, that is like EM is nothing but, electromigration is nothing but how long your power mesh is durable. That is EM check. That is nothing but reliability. This is what in power planning we have to take care all about EM as well as your airdrop. That's all about the power planning. Thank you so much.